Photon states are states of the electromagnetic field. They're quantum states of the electromagnetic field. A photon, this particle, is a quantum of the electromagnetic field. It's a discrete piece of energy and momentum carried by this particle. So when we talk about photon states, we're really doing quantum field theory. So in some sense, this lecture, you will see how quantum field theory works. A first introduction to quantum field theory. It's interesting that the harmonic oscillator plays such an important role on that. So a key identity that we're going to use, of course, is this coherent states that were defined as displacements of the vacuum, where D, if I remember right, was e to the alpha A dagger minus alpha star A. And it had the property that A acting on alpha was equal to alpha, alpha, the operator A. So these were the coherent states we've been talking about. And today we're going to talk about photon states. Photon states have to do with electromagnetic fields. That's electric and magnetic fields. And one important quantity that you know about electromagnetic fields is the energy. If you have an electromagnetic field, you have an energy. And remember, energies have to do with Hamiltonian. So we're going to try to do a quantum description of the electromagnetic field. Therefore, knowing the energy would be a good place to start. So the energy, as you know, in an electromagnetic field goes like E squared times some epsilon and B squared. And you add them, the two of them. So here we go. Let me write a precise formula. The energy is equal to 1/2 the integral over volume, epsilon 0, the electric field squared, plus C squared times the magnetic field squared. So this is our energy. And we're going to try to describe a configuration of electromagnetic fields. We will focus on one mode of the electromagnetic field. So I will imagine I have some sort of cavity, finite volume. And in there, I have one electromagnetic field, what you usually called in 802 or in 8022 or 807, a wave. A single wave with some wavelength, some frequency, and that's all we have. So we're going to simplify to the case where we have a single one, consistent with Maxwell's equations, and some boundary conditions that we need not worry about. And I will normalize them as follows, with a V in here that is the volume of the system. So volume. And that could be the volume of a cavity that has this electromagnetic field, or some large box, or you can let it almost be infinite and work with that as well. So we'll have a wave, omega will be the frequency, k is omega over c for a electromagnetic wave. So we'll have this times omega sine of kz, a spatial distribution. And there will be a function of time, as you know. But this function of time, I want to leave it a little ambiguous at this moment, or general, not ambiguous, general. So I'll call it q of t, some function of time to be determined. there's going to be an a magnetic component to this field, By. C times By will also depend on Z and T, and will have the same prefactor. I put a C here so that the C squared B squared also works well. Epsilon 0 V. This time I'll put another function, P of T, cosine of Kz. It's another function of time, and I just call them that way. There is a question there.
Why is your frequency outside your function of time?
It's just another constant here.
What does that mean?
No particular meaning to it. At this moment, whatever this constant is, you would say probably it's useful because you somehow wanted a Q here that has some meaning. So you probably would put the same constants here, and first trial, you wouldn't have this omega here. But if you put it, this is just another way of changing the normalization of Q. So it doesn't have a profound meaning so far. Any other questions about this? This is an electromagnetic field configuration, and this Q of T and P of T are functions of time that you know your Maxwell's equations, and you will check things related to Maxwell's equations for this configuration in the homework, but that at this moment is not too crucial. The thing that is important is that we can try to calculate the energy now. And if you do it, well, the squares, the epsilon zeros are going to disappear. And you're going to have to integrate over the box. This integral of sine squared of kz or cosine squared of kz, the functions of time don't matter. This energy could depend on time. And the way we've prepared is when you integrate over sine squared of kz, if the box is big, it's a good situation where you can replace that for 1/2, which is the average, and 1/2 for the average of this. Or you could define what z, where the box extends from what values of z to what other values of z's. And so the integral, in fact, is not any complicated integral, and we have immediately the answer that energy is 1/2 p squared of t plus omega squared q squared of t. And that was why this omega was here. There's not really much to this, except that when you square it and you take the integral over the volume, you replace the sine squared by 1/2 and the cosine squared by 1/2, and that's it. So actually, the labels that we've chosen here are pretty good. This starts to look like a harmonic oscillator, except that the mass is gone. 1/2m p squared should be plus 1/2 m omega squared q squared. So the units are wrong here. P squared over 2m has units of energy, but p squared doesn't have units of energy. And 1/2 m omega squared q squared has units of energy, but this one doesn't. So the units are a little off for a harmonic oscillator. So it's interesting to notice now, but you couldn't have done better because photons have no mass. And we're trying to describe the electromagnetic field. It has photons, so there's no way this could have showed up a mass there. There's no such thing. And that's why it doesn't show up. On the other hand, you can say, well, okay, let's see if this makes a minimum of sense. How do we deal with these units? So P has units of square root of energy. And Q has units of time times square root of energy. Why is that? Because omega has units of 1 over time, so Q over time squared is energy, so Q is T times square root of energy. And therefore, P doesn't have the right units to deserve the name P, and Q doesn't have the right units to deserve the name Q, but P times Q has the units of time times energy, which are the units of h bar. So that's good. These P and Q have the right units in some sense.